with GPSX, looking at one of our particular unit processes, for example. However, today what we're going to do is start very much from the basics and take a look at, starting at the beginning, what can we do with an activated sludge model, how is it useful to us, and then I'm going to start from a completely blank page in GPSX and show you how to build a wastewater treatment plant model. We'll run some simulations and generate some output, and I'll answer questions at the end as well. So as you can see in your GoToWebinar dashboard, there's a spot where you can ask questions. So you can type those in as we go along, and then usually what I like to do is answer them in a little live question and answer period at the end. Okay, so I'm going to get started. So just to introduce myself, if I haven't met you before, my name is Spencer Snowling. I've been with Hydromantis for almost 14 years now, and I've been the guy that's been in charge of the development of GPSX for about the last 12. And I'm happy to be here today to do this webinar and demonstrate the software to you. So my plan for today is to talk first a little bit about modeling itself. You know, why is it a useful tool? What can I do with it? How can it benefit me when I'm doing my engineering tasks and investigations of wastewater treatment plant models? I'll talk a little bit about the activated sludge model basics, sort of what's in the in GPSX behind the scenes. This could, of course, be a full 2 or 3 day course, so I won't be going into a lot of detail there, but just to give you a little taste of what's going on behind the scenes in GPSX. And then, as I mentioned, I'm going to go do a live demonstration from my desktop here of how to set up a model, how to enter in some information about that plant itself, to run a simulation, and to generate some output, and then get that out to an Excel spreadsheet. And then lastly, I will answer any questions that you have. And as I mentioned, you can type those in the questions box as we go. Okay, so why do we use modeling, or why do people in this industry find modeling to be a useful tool? So in most cases, what is happening is the GPSX model is going to stand in for the real wastewater treatment plant model, and allow you to do testing and investigate its behavior in a way that you couldn't do with a real system, either because it's not possible or because it's too expensive. So that's probably the biggest essence of modeling in general, is to be able to do an investigation on a plant without actually having to do it in reality, and do it in a way where you have a lot of control over what it is that you're trying to understand. For the most part, it's easier, obviously, building a treatment plant on your desktop and running some simulations. You can load it up with whatever type of influent you like. You can have whatever kind of wet weather event that you like. You can do stress testing. You can investigate different operational scenarios. And for the most part, that's all easier to do in a model than it is to do in reality. And of course, the model is there because you want to find out what the capacity is. You want to understand what the behavior of that plant is when things are going bad. So using a model is also risk-free. You can fail that plant all you like. Nobody's going to come by and charge you, obviously. So people like to be able to do stress testing in the model first, because that gives them a rough idea of where that plant is at in reality. And the other reason is, of course, you get results quickly. So if, for example, you were going to change your wastage at your wastewater treatment plant, and you wanted to see what effect that was going to have on the mixed liquor or the SRT, if you make that wastage change, it's probably going to take several days or even a couple of weeks before you fully see that system come into equilibrium. Whereas in the model, of course, you get that answer pretty much right away. So for the most part, the way that we see our clients using this software, and the way that we indeed use it ourselves when we are doing projects for our own clients, is that we start by creating a model of a wastewater treatment plant in GPSX and entering in all of that information about the tank sizes and the clarifier depths and so on. And then we go through a process of calibration of that model. So we calibrate it to known performance. We get some historical data from that plant. We run some simulations, and we plot the model results alongside the known data, and then we sort of tweak the numbers and dial in some of the lesser known values in the model and try to bring that in so that it's predicting something that we know to be true. Then what most people like to do when they're investigating the behavior of a wastewater treatment plant is to simulate what they call their base case. So this is sort of the standard running, normal, typical operation of your wastewater treatment plant. And quite often I see, particularly here in Canada, we quite often do a summer base case and a winter base case, given the wide range of temperatures that we have to deal with here. So once that's done and you've established what your base case is, then you simulate your different scenarios, and that could be anything depending on what your question is that you're looking into. So you may be running at different SRT, you may run it under different operating procedures, try different influence, and whatever those questions are that you're asking of the model. And then once that's done, you compare those two things together to see what the difference is in that performance. So that's sort of modeling in a nutshell right there. Is you set up a model, you calibrate it so that it's representative of that real wastewater treatment plant and that specific plant, and then you run some simulation scenarios to investigate what happens if I make a change to this plant, and where am I going to be, and is that going to make us better or worse? So with respect to what's going on under the hood, so to speak, with GPSX, there's so much detail here. As you know, each one of these individual unit processes has a model behind it, even the influent model. So each one of these processes takes the information from upstream, and then it does whatever calculations it's supposed to do, depending on what that individual unit process is, and then it passes that other information back downstream onto the next object, and then we solve all of that information and all of those predictions for the whole plant altogether. So rather than go into a lot of detail about everything that's here, I'm just going to focus on the aeration basin here. This is really where much of the most valuable part of GPSX is in order to do a prediction of activated sludge process, which is a very complicated process with lots of recycles and lots of different types of biomass and processes going on. There is quite a lot going on in this individual process. This is a plug flow tank that we're showing here with some flow coming in. We can distribute that either in the front end of this plug flow system, or we can do some step feeding. We've got bubbles here to represent the aeration that's going on. There's really a lot happening here. There's, and in fact, 6 submodels going on most of the time in this particular unit process. We have a hydraulic model. Almost all of our models have some sort of hydraulics in there to describe the flow of the liquid through the system. So we may have some pumping happening. We may have some internal recycles that move some flow from one section to another, from an aerated section back to an anaerobic section, for example. So we have to keep track and do all that flow balancing as things go along. We also have an aeration model. So that's basically there to do the mass transfer of oxygen through our gas transfer model that will tell us what is the amount of oxygen being provided to this system based on that diffuser grid or mechanical aerator, depending on what you have. We did quite a lot of work in this aeration model in version 5 of GPSX, and we've continued to update that since. We feel it's quite robust, and it does a decent job of being able to tell you, well, if I specify a certain amount of airflow, then how much flow am I getting, how much oxygen transfer is happening, and then how much residual DO do I have left in my system. Then, of course, we have the biological model itself. This is probably the most detailed part of GPSX, is looking at the biological model. And so, for example, we have our in-house Mantis model, and that describes the transformation of nitrogen and carbon and in some cases phosphorus. And those are there to take a mechanistic approach and look at all the different biomass types and deal with their growth and their death, and there's hydrolysis and transformation of other kinds of nitrogen and alkalinity and so on. So there's several dozens or even hundreds of equations to describe the transformation of all those different kinds of things in our biological system. And we then, on top of that, in certain models, our more complex models in GPSX, have a few other things in there too, including a gas transfer model for our greenhouse gas emissions portion of GPSX. We have a pH model there to do inorganic speciation of a number of different types of ions in our system. We also do mass balances on calcium and magnesium and potassium and so on. And then for those ones where we have a pH model, we also have a chemical precipitation model. So for things like struvite, we can take that information from the inorganic part of the model and calculate how much is being precipitated out. So I could probably do a webinar on each one of these things individually, We may do that someday. So just to let you know that there's a whole lot of calculations and modeling going on in the background for each one of those individual unit objects that you have down on your drawing board. The biological models, as I mentioned, are probably the place where, there's really the most power in GPSX, is to be able to, predict the behavior of an activated sludge system under any kind of loading at any temperature and any kind of operational system. And so these models were basically developed by the IWA task group on activated sludge modeling, starting back in the mid-'80s and continuing through into the '90s. This is sort of the main suite of models that they developed that was sort of kicked off the wastewater treatment industry, ASM1 and ASM2 and so on. Now, these models are all available for you to use in GPSX. However, we have developed our own models, Mantis and Mantis 2 and Mantis 3 and so on. These are there to be able to sort of build upon this fundamental building blocks that we're starting with the group, the work that was done by this group a couple decades ago. So most of the models in our industry across the board are all come from this sort of ASM1 approach, where you break things down into individual growth and depth and hydrolysis processes. So if you take our training course, we go into this in more detail. So what I thought I would do is just talk a little bit about what the top uses of GPSX are as we know them. So we do, a fair bit of work to use our software and, provide services, professional services to our clients. And so we use our software in-house, and we know what our clients are using it for. So I summarized these down to a single slide here. For places where there's design going on of a wastewater treatment plant that hasn't even been built yet, and we do quite a bit of modeling of treatment plants that are still in the design stage, this is a good opportunity to use modeling to compare various process configurations. So should I be using, a Bardenfo or Johannesburg or an A2O process to do my BioP? Those types of questions can be answered and addressed quite well in the model. For models, for wastewater treatment plants that already exist, probably the number one use of GPSX is to verify plant capacity. So basically, people operating a plant and it's running, and they want to know how close they are to their limit. So we build a model, we calibrate it, and then we start increasing the load and running simulations where we increase the load to find out, where is that limit at which they lose nitrification or they lose treatment altogether. Quite frequently, we are retained to come in and use our software to do a cost-saving investigation using a model. So that's basically looking for opportunities where we can look at changing the operation of that plant. And we are looking for an opportunity to get the same kind of treatment while using less energy or less chemical dosage. And so there's a good opportunity to use modeling there, because you can run a number of simulations of different strategies and compare and try to refine and use the best opportunities that are available given the operation and loading to your plant. So in places where that's kind of been done, or places where we've done a capacity analysis and we found that, when the plant sort of gets close to its capacity and it starts to fail, it is very easy and useful with a model to identify where that bottleneck happens. Or another way to think of it is, which part of my plant do I run out of capacity first? Am I limited by my aeration system, or am I going to run out of clarifier capacity, or my digester is going to be my limiting part of my plant? So that's another frequent use of modeling. We also, for those plants that are reaching their limit, are used quite often to evaluate retrofitting a plant. So model up a plant that has a particular limitation, and then run some simulations where we convert something to an IFAS or MBBR or membrane bioreactor, and then try out those options in the model to see what the opportunities are to be able to retrofit and increase the capacity of that plant. And lastly, we've been involved with a number of simulations recently which involved sort of forensically analyzing an event that happened and doing it sort of after the fact to determine whether the actions that were taken at that time were appropriate, or whether something different could have been done that would have been better. So modeling is quite useful to be able to sort of go back and say, what would have happened if I had done something different than what I did? And you can compare your actions with your other potential actions and find out which would have been the best thing to have done. So that's sort of a run through of sort of the top 5 or 6 things that GPSX is using, and maybe one of those might be something that is valuable to you. Okay, so what I'm going to do right now is move out of the talking phase and into the actual demonstration phase here. And I'm going to be showing you GPSX version 6.2. So as you may know, we release a new version of GPSX every fall, and we're working on version 6.3 right now. So this is version 6.2. Hopefully you've had a chance to take a look at it before, and if not, I'll just give you a brief tour here. The wastewater treatment plant model is built on this blank drawing board here by using these individual unit processes on the left-hand side. So we are quite proud of our library of wastewater treatment plant models. We feel it's the sort of some of the most sophisticated and sort of wide-ranging library of unit processes, hopefully to cover off every type of wastewater treatment plant that you may encounter in your work. So what I'm going to do is start out by building a very simple model. You don't always model the whole plant for every project. I'm going to build just the activated sludge portion of the plant for this demonstration right now. So this is an influent object that is going to describe the flow that's coming into the plant. This is a activated sludge unit, a plug flow tank, as I mentioned before, and then we're going to use a circular secondary clarifier. So I'm going to zoom in here a little bit. Okay, and then once you've dropped those on the board, you can then hook these things together just by dragging and dropping these connections. And so here's our RAS line coming back around to the head of the plug flow tank. And then once that's done, you can right-click on these objects to open up their menus. And in most cases, what you're going to want to do is, specify the information that you have about the physical and operational characteristics of these individual unit processes. So in this case, I can enter in the volume of this tank. You can work in whatever kinds of units that you like, in millions of gallons or meters cubed or whatever. And you can specify its size and depth and temperature and so on. The other thing to do is specify how this unit is going to be operated. And so in this case, we can see here, for example, that this has a DO controller on it specifying the amount of airflow. Well, I'm going to change that just for the demonstration and enter in the airflow that I want to use, and this will remain constant through the simulation. So I'm going to use 20,000 meters cubed per day. By the way, you can make notes here as you go along putting your model together. This is sort of a handy way to document what you've done so that you'll know when you come back to it later. That will always be there and also get output to the reports as we go along. You can see them by just putting your cursor there. So once you've done that, you've entered in all of the flow rates and recycle rates and wastage rates and so on, and specified all the incoming concentrations in your influent. You can go to simulation mode here. So this now puts us in a spot where this model is going to be built, and this is our Fortran compiler at action there. We use Fortran because it's robust and very fast. And we've now got an environment here where we can set up all of the input and output that we want for running this simulation. So the input kind of goes up on the upper left corner here, and I'm going to just open this menu that allows me to specify the influent flow. And you can actually drag that directly here and make yourself what we call a slider. It's a small tool that allows you to just intuitively move the values around or type them directly in that box. It gives you a nice interactive way to interact with the model. So right now we need some output over here to look at. If I double click on an object, I can get a new tab here with all of the information for that particular object, and it's specific to that object. And so if I run a simulation right now, you go to the lower left-hand corner and hit Start. This little table specifies all of the details that are for this particular unit processes, mixed liquor, and nitrogen and phosphorus and BOD and COD and so on. Some other details about the aeration and little mass balance at the bottom there. And if you go to the clarifier page, where you get stuff that's specific to the clarifier, like sludge blanket height and so on. I'm going to open up a couple of other tabs here just to specify some more, usually the type of things you want to look at when you're doing an investigation here. So I'm going to plot the profile. So this is going to be a bar graph that will show the concentrations through the length of that plug flow reactor. So let's look at oxygen and phosphate, and let's look at ammonia and nitrate. So this is, the kind of output that you'd construct if you were doing a typical nutrient removal investigation with a model. And if I rerun that simulation here, you can see that, this is the front end of the plug flow tank, and this is the back end, and our oxygen is sort of depleted at the front, and it's sort of higher, almost 4 milligrams per liter at the back end. So these are the ways that you investigate, how that plant is going to perform, and it's going to predict what the concentrations are. So just to summarize here, even though we've got some depressed oxygen at that front end of the tank, we are getting pretty much full nitrification here. This is the ammonia going down as it goes through the length of the tank, and we're generating some nitrate here, of course. And, well, we're not really doing any significant BIOP removal in this particular case. So what I'm going to do then is also plot some effluent quality and run a dynamic simulation. So let's look at total suspended solids, BOD, COD, TKN, the sort of things that you might plot for an effluent. And I'm going to run a 50-day simulation here. And if I, let's take a look at our profiles. If I run that and then I change while the simulation is running, if I change the loading to the plant, I'm just increasing that flow. We can see here that, while keeping all other things the same, we're not nitrifying anymore. We've lost nitrification as that load increased. So I'm going to move this back to where nitrification will come back. If we look at our dynamic effluent plot here, we can see, just rescale the graph there, that we lost nitrification, and we see the impact on the effluent quality while that large loading was happening at that plant. So this is a dynamic simulation. You can do your own wet weather events. You can do your own, dynamic stress testing and so on by entering in information here. You can either do it manually with your mouse, or you can even have GPSX read in a file that will have a time series of information and will move that knob around for you. So lastly, I'll just mention how you get the information out of here. You click on this button here to generate a report. It is a spreadsheet report. We just with one click of the button, we export out all the information and all the graphics for you into this Excel spreadsheet. And we have a different tab down here for each of those graphs that created, and you can see the data is shown below. And that can be all taken out and used in other reports and so on. So this is sort of the general use of GPSX, the way that you use it by building a model, by entering in the information, by running simulations, and then taking that output and then putting it in a format that you need for the rest of your work. So that's sort of a very basic run through the software. And I'm going to go back to my slides here. What I just did was actually more or less tutorial 1 of GPSX. So if you'd like to see more about how you go through the steps of setting up a model and using some of our more advanced functions, setting up scenarios to do sensitivity analysis and optimization and so on, you can come to our website, hydromantis.com, and click on the videos section, and then go to the tutorial videos section here, and then we have all 11 tutorials from our website have been carried out here for you to watch. So some other things you may want to try with your version of GPSX, just to get a feel for what can be done. Quite frequently, people like to set up 2 wastewater treatment plants in one layout and then compare the options side by side. That's sort of a common use. You have a single influent that you split between the 2 plants, and then you can investigate and compare them nicely and easily side by side under different loading conditions. You can take a look at using a dynamic file input to run different types of wet weather events through your plants. So that's actually tutorial 4, where you specify, you can take some real historical data if you like, or you can enter in your own information. When you run the simulation, the knobs move around on their own to increase and decrease flows and concentrations, and pretty much anything else that you want, any other parameter can be done in GPSX the same way. So you can try out investigating some PID control loops. What if we had a different type of DO controller, or what if we were doing ammonia control, or mixed liquor, sludge blanket height? You can try any of those types of dynamic PID control loops in GPSX. And you can try different strategies for taking units offline. If you have a complex plant that allows you to take individual units out, and you have things in parallel or in series, you can do that with GPSX and investigate what happens when you do that to find out what's your optimal strategy for or construction schedule, for example. Okay, so that's sort of 25 minutes here, the sort of the basics of what I wanted to cover today. I'm going to show you a few slides here about things that we've got going on at Hydromantis right now. And then after that is done, I will answer any questions that you have. If you want to type them in the box there, see we've got one so far. I'll answer those questions live when we're done. So as you may know, we have a new YouTube channel. So if you go to youtube.com/Hydromantis, you can find all of the videos. They're the ones that I was also mentioning on our website. In addition to GPSX tutorials, there's also other helpful videos about how to manage your license on GPSX, change your key code, and so on. And also all of our other pieces of software as well, ToxCam and CapTetWorks, all of the tutorials and other things and other explanatory videos about how things work. And on top of all of that, we have all of the recordings of our webinars too. There's actually quite a few hours of webinars there available at this moment, and you can go investigate that at your leisure. We also offer online training using this GoToWebinar service. So we can provide GPSX or ToxCam training to you over the internet, and we go through our very basic, and we can even do more advanced training as well, and we can do that over a period of a day or two using this service. If you're interested, please let us know. I'll mention that we are right at the very end of the development of the newest version of ToxCam, version 4.2, so keep your eye out. You'll be getting some information about that release shortly. I've been working through the summer here on the new version of GPSX, version 6.3. We've got some new unit process models coming. An alternating aeration ditch type of model is coming. Also some new data analysis features. And that's coming out this fall, and we're just getting underway with a new version of CapTetWorks, version 3.0, and that will be a fairly major update to that piece of software as well. So we have another upcoming webinar that I hope you can join us for. It's on July the 18th at 2 p.m. Eastern Daylight Time, and it will be on setting up PID control loops in GPSX, how to set them up, how to tune them, how to take advantage of their sophisticated nature and try to use them and doing them in cascade and so on. We're going to try and investigate all the different options with GPSX, and again, we'll be answering live questions as well. So I'd like to thank you. If you can hang around, I'll answer a couple of questions, and if not, then if you have any other further questions or information, please feel free to email me at my last name, snowling@hydromantis.com. We're also looking all the time for new ideas for webinars. If you have a particular topic that you would like us to cover, please either type it in the questions box today or send me an email.